somewhere in the quiet hours, when the machines sleep and the servers hum their electric lullabies, there exists a graveyard of mistakes. Not a graveyard of stone and earth, but one built from ones and zeros, from miscalculations and oversights, from the small decisions that cascaded into catastrophes. Tonight, we drift together through the shadows of history's greatest software failures, where billions of dollars evaporated in moments, where lives were lost to invisible errors, and where the hubris of human ambition collided with the unforgiving precision of code. The year is 1996, and above the Atlantic Ocean, a rocket is climbing toward the stars. It carries within its metal shell the dreams of engineers, the hopes of scientists, and 4 satellites worth hundreds of millions of dollars. The Ariane 5 rocket, Europe's pride, ascends through the clouds with perfect grace. 37 seconds pass, 38, 39, and then, in the 40th second, something impossible happens. The rocket begins to tear itself apart, not from any mechanical failure, not from any fuel leak or structural weakness, but from something far more insidious. A single line of code inherited from an older rocket tries to squeeze a number too large into a space too small. A 64-bit floating point value attempts to fit into a 16-bit integer. The overflow cascades through the system. The backup computer, an identical twin, fails in exactly the same way just 72 milliseconds later. The rocket's guidance system interprets error messages as flight data, believes the rocket is veering off course, and fires correction thrusters that send it into a violent spin. $370 million worth of technology explodes in a fireball over the ocean, all because someone forgot to check if a number would fit. This is not a story about incompetence. This is a story about the terrifying fragility of the digital world we have built, about how the smallest assumptions can lead to the largest disasters, about how in the pursuit of efficiency and progress, we sometimes forget to ask the most basic questions. The Ariane 5 failure stands as a monument to a truth we often ignore. That software, invisible and weightless as it seems, carries within it the power to destroy fortunes, end lives, and reshape industries in the blink of an eye. The engineers who wrote that code were not fools. They were experts, seasoned professionals who had built successful rockets before. But they made an assumption. They assumed that the flight characteristics of the Ariane 5 would be similar enough to the Ariane 4 that the old code could be reused. They assumed that certain variables would never exceed certain ranges. They assumed wrong. Let us drift back further to the closing years of the 20th century, when the world held its breath and waited for midnight. The year 2000 problem, known simply as Y2K, loomed over civilization like a digital sword of Damocles. For decades, programmers had saved precious memory space by storing years as 2 digits instead of 4. 1975 became 75. 1983 became 83. It was a small optimization, born from an era when every byte of memory was precious, when storage was measured in kilobytes and computers filled entire rooms. But as the millennium approached, a terrifying realization spread through the computing world. When the calendar rolled over to the year 2000, systems everywhere would read it as 1900. Financial systems would calculate interest incorrectly. Power grids might fail. Air traffic control systems could collapse. Nuclear weapons might misfire. The economic impact of preparing for Y2K was staggering. Estimates suggest that the global cost of remediation exceeded $300 billion, with the United States alone spending over $100 billion. Banks hired armies of programmers to comb through millions of lines of ancient code written in COBOL, a language from computing's Jurassic period. Governments established task forces, companies stockpiled supplies, Survivalists built bunkers and hoarded food. The irony, of course, is that we will never truly know how catastrophic Y2K would have been if nothing had been done, because something was done. Vast resources were mobilized, countless hours were spent, and when midnight came, the transition was relatively smooth. Some point to this as evidence that Y2K was overblown, a mass hysteria that wasted billions on a non-problem. Others see it as proof that the investment was necessary, that disaster was averted through diligence and foresight. The truth, as always, lies somewhere in the shadowy space between. What we do know is that the economic impact was real. $300 billion spent to fix a problem that should never have existed in the first place. A problem created by small decisions made decades earlier by programmers who never imagined their code would still be running at the turn of the millennium. But not all software failures announce themselves with such apocalyptic fanfare. Some slip in quietly, kill silently, and are only discovered when the bodies begin to pile up. In the mid-1980s, a medical device called the Therac-25 promised to revolutionize cancer treatment. It was a radiation therapy machine, computer-controlled, designed to deliver precise doses of radiation to tumors while sparing healthy tissue. Previous models had used hardware interlocks, physical mechanisms that prevented dangerous configurations. But the Therac-25 was different. It was modern. It relied on software for safety. Hardware interlocks were expensive, bulky, and seemed unnecessary when code could do the same job faster and cheaper. Between 1985 and 1987, the Therac-25 killed at least 3 people and injured 3 others, delivering radiation doses more than 100 times stronger than intended. The victims described feeling an intense electric shock. Radiation burns appeared on their skin days later. Some died quickly. Others suffered prolonged, agonizing deaths as the radiation destroyed their tissue from within. The cause was a race condition in the software, an invisible flaw that only manifested when a specific sequence of keystrokes was entered at exactly the right speed. One radiation technician had become so proficient at operating the machine that she could enter commands faster than the programmers had anticipated. When she corrected a mistyped entry, the software would set the beam to high power for X-ray mode, but then failed to engage the spreading magnets that would distribute the radiation safely. Instead, a concentrated beam of electrons meant to be diffused and weakened struck patients at full strength. The software displayed malfunction 54 on the screen, a cryptic error that the technicians had learned to ignore because it appeared frequently and usually indicated nothing serious. So they would reset the machine and continue treatment, not knowing that they were killing their patients one dose at a time. The Therac-25 disaster revealed a fundamental truth about software-dependent systems. When hardware interlocks were removed and replaced with software checks, a new kind of vulnerability was introduced. Hardware fails in predictable ways. A physical interlock either works or it doesn't. But software fails in strange emergent ways, in patterns that appear only under specific conditions, in race conditions and edge cases that are impossible to fully test. The programmers who built the Therac-25 had actually copied code from an earlier model, the Therac-20, which had the same race condition bug. But the Therac-20 had hardware interlocks that prevented the bug from ever causing harm, so the flaw went undetected. When that code was transplanted into the Therac-25, which lacked those physical safeguards, the invisible bug suddenly became lethal. This pattern of reusing code, of assuming that because something worked in one context it will work in another, appears again and again in the history of software failures. Fast forward to August 1st, 2012, and the opening bell of the New York Stock Exchange. Knight Capital, one of the largest trading firms on Wall Street, had just deployed new software designed to handle trading in the retail liquidity program. What happened next unfolded at the speed of algorithms, far too fast for human intervention. The new software had been installed on 7 servers, but on one server the installation was incomplete. When the market opened, that server began executing trades using old code, a retired algorithm called PowerPeg that was supposed to be dormant. In 45 minutes, Knight Capital bought and sold 150 different stocks, accumulating positions worth $7 billion. The trading was erratic, irrational, sending stock prices into wild swings as Knight's computers bought high and sold low over and over and over, hemorrhaging money with every transaction. By the time engineers identified the problem and shut down the system, Knight Capital had lost $440 million. In less than an hour, a software glitch had wiped out nearly 4 times the company's quarterly revenue and destroyed 75% of its market value. The company's stock plummeted. Emergency financing had to be secured just to keep Knight Capital from collapsing entirely. Eventually, the firm was acquired by a competitor at a fraction of its former value. $440 million vanished in the time it takes to eat breakfast, because someone forgot to fully deploy new code to all the servers, because the old code was still present and accessible, because the chaos unfolded faster than any human could comprehend or stop. The Knight Capital disaster illustrates the unique terror of automated trading, of systems that execute thousands of transactions per second based on algorithms that respond to market conditions in microseconds. When these systems fail, they fail catastrophically and instantly. There is no time for a human to step in, no moment of pause where someone can say, "Wait, something is wrong." By the time anyone realizes what is happening, millions or billions of dollars have already changed hands. The engineers at Knight Capital faced a nightmare scenario. Their first instinct was to roll back the code to the previous version, assuming the problem was in the new deployment. But that made everything worse, because it was actually the old code causing the chaos. They were pouring gasoline on a fire, thinking they were fighting it. The incident sent shockwaves through Wall Street and prompted new scrutiny of high-frequency trading and the risks of fully automated systems. Let us drift now to the autumn of 1999 and the red deserts of Mars. The Mars Climate Orbiter has travelled 416 million miles over 9 months, carrying instruments designed to study the Martian atmosphere and climate. As it approaches Mars, ground control prepares for the critical orbital insertion maneuver that will slow the spacecraft and allow it to be captured by Mars's gravity. But something is wrong. Telemetry data suggests the orbiter is approaching too close to the planet, far closer than planned. Engineers scramble to understand what is happening, but there is no time. The spacecraft is moving too fast, travelling too far. It descends to an altitude of just 57 kilometers above the Martian surface, when it was supposed to maintain a safe distance of 150 kilometers. At that altitude, atmospheric friction is too strong. The Mars Climate Orbiter, worth $327 million, either burns up in the Martian atmosphere or skips off into space, lost forever. The investigation revealed a mistake so simple it seemed almost absurd. The software that controlled the spacecraft's thrusters had been developed by Lockheed Martin and calculated force in English units, pounds of force. But NASA's navigation software expected those values to be in metric units, newtons of force. For 9 months, as the spacecraft travelled through space, the navigation calculations were off by a factor of 4.45. Every course correction was slightly wrong. Every trajectory calculation accumulated more error. And because the two teams didn't properly verify that their software interfaces matched, because no one did an end-to-end test of the entire system, because everyone assumed that of course everyone else was using metric units like the specifications required, the mistake went undetected until it was too late. $327 million burned up in the Martian atmosphere because someone forgot to convert pounds to newtons. The disaster became a textbook example of the importance of interface verification, of the dangers of assumptions, of what happens when different teams work in isolation without rigorous integration testing. The investigation board noted that several warning signs had appeared during the mission, small anomalies in trajectory data that hinted at problems. But communication breakdowns between different elements of the operations team prevented anyone from connecting the dots. The people who noticed the anomalies didn't have access to the people who understood the spacecraft's design. The people who understood the design didn't see the telemetry data. Everyone was looking at pieces of the puzzle, but no one stepped back to see the whole picture. And so the Mars Climate Orbiter sailed to its doom, a victim not of mechanical failure or cosmic bad luck, but of human error and organizational dysfunction. These stories share common threads. They are tales of assumptions gone wrong, of code reused without proper verification, of systems grown so complex that no single person understands how all the pieces fit together. They are stories of optimization and efficiency pursued at the cost of safety and redundancy. They are warnings about what happens when we trust software without questioning it, when we remove human oversight in the name of speed and automation, when we forget that the invisible world of code has very real consequences in the physical world. The Ariane 5 explosion, the Y2K panic, the Therac 25 deaths, the Night Capitol collapse, the Mars Climate Orbiter loss. These are not isolated incidents. They are symptoms of a deeper condition, a fundamental tension in how we build and deploy software in a world that has become utterly dependent on it. Consider for a moment the architecture of trust we have constructed. Every time you board an airplane, you place your life in the hands of software you cannot see. Every time you withdraw money from an ATM, you trust that the code running somewhere in a data center will accurately track your balance. Every time you undergo medical treatment, you assume that the machines administering your care have been properly programmed. This trust is largely warranted. Most software works most of the time, but the failures, when they come, reveal just how precarious our position really is. We've built a civilization on foundations of code, and those foundations are riddled with cracks we cannot see until they give way beneath us. The Boeing 737 MAX stands as perhaps the most devastating example of software failure in aviation history, a disaster that killed 346 people in 2 separate crashes and grounded an entire fleet of aircraft for nearly 2 years. The story begins not with the crashes themselves, but with a corporate decision made years earlier. Boeing, facing fierce competition from Airbus, needed to upgrade its workhorse 737 design to compete with newer, more fuel-efficient aircraft. But a complete redesign would take years and cost billions. Pilots would need to be retrained, certifications would need to be obtained. Instead, Boeing opted for a faster, cheaper solution. They would retrofit the existing 737 design with larger, more efficient engines. The problem was that these larger engines had to be mounted further forward and higher on the wing to provide ground clearance. This changed the aircraft's aerodynamics, making it prone to pitch up dangerously in certain flight conditions. To compensate for this aerodynamic quirk, Boeing developed a software system called MKS, the Maneuvering Characteristics Augmentation System. MKS would automatically push the nose down if sensors detected that the aircraft was approaching a stall condition. On paper, it was an elegant solution. In practice, it was a catastrophe waiting to happen. The MCAS system relied on data from a single angle of attack sensor with no redundancy. If that sensor malfunctioned and reported incorrect data, MCAS would activate when it shouldn't, forcing the nose down even though the aircraft was flying normally. And critically, Boeing decided not to tell pilots about MCAS. It was not mentioned in training materials. It was not included in flight manuals. The company wanted to market the 737 MAX as essentially identical to previous 737 models, requiring minimal additional training because that made it more attractive to airlines. On October 29, 2018, Lion Air Flight 610 took off from Jakarta, Indonesia. 12 minutes later, it plunged into the Java Sea, killing all 189 people aboard. On March 10, 2019, Ethiopian Airlines Flight 302 took off from Addis Ababa. 6 minutes later, it too crashed, killing all 157 people on board. In both cases, a faulty angle of attack sensor fed bad data to MCAS. The system activated, pushing the nose down. The pilots, unaware that MCAS even existed, fought to keep the aircraft level. They pulled back on the controls, but MCAS kept activating, repeatedly forcing the nose down. Eventually, they lost control. The crashes triggered a global grounding of all 737 MAX aircraft. Investigations that exposed systemic problems in Boeing's development and certification process, criminal charges, billions of dollars in fines and compensation, and a permanent stain on Boeing's reputation. The economic impact of the 737 MAX disaster has been estimated at over $20 billion when accounting for the grounding costs, compensation to airlines and victims' families, lost sales, production delays, and fines. But the true cost goes beyond money. Trust in Boeing, once seen as synonymous with aviation safety, was shattered. The Federal Aviation Administration certification process was exposed as having been essentially outsourced to the very company it was supposed to regulate. The crashes revealed that in the race to compete with Airbus, in the drive to cut costs and speed up development, Boeing had compromised on safety in ways that would have been unthinkable in earlier eras of the company's history. Engineers warned that MCAS needed more safeguards, that relying on a single sensor was dangerous, that pilots needed to be informed about the system. Their warnings were overruled or ignored. The software development was partially outsourced to contractors being paid as little as $9 an hour. A shocking revelation for a system whose failure could kill hundreds of people. The 737 MAX disaster illuminates a disturbing trend in modern software development, the relentless pressure to cut costs and accelerate timelines even when lives are at stake. Boeing's management made decisions that prioritize short-term profits and competitive positioning over long-term safety and quality. They gambled that MCAS would work well enough, that a single sensor would be sufficient, that pilots wouldn't need to know about the system. They lost that gamble, and 346 people paid with their lives. The crashes also highlight the danger of automation opacity, of creating systems that intervene without pilots' knowledge or understanding. When MCAS activated and began forcing the nose down, pilots didn't know what was happening or how to override it. They were fighting an invisible enemy, a piece of software they didn't know existed following logic they couldn't comprehend. Let us turn now to a different kind of failure, one that unfolds not in seconds but over years, one that demonstrates how software disasters can be disasters of scale and ambition as much as disasters of code. In October 2013, the United States government launched healthcare.gov, the website for the Affordable Care Act's health insurance marketplace. It was supposed to allow millions of Americans to shop for and enroll in health insurance plans. Instead, it became a catastrophic failure of government technology, a public embarrassment that threatened to undermine an entire piece of legislation. On launch day, the website collapsed under load. Users couldn't create accounts, pages wouldn't load. The system crashed repeatedly. Of the 250,000 people who tried to visit the site on its first day, only 6 were able to successfully enroll. The problems were numerous and deep. The system had been built by multiple contractors working on different components, but no one had properly tested how all those components would work together. The database couldn't handle the load. The front-end interface was poorly designed. The back-end systems that connected to insurance companies and government agencies were buggy and unreliable. Critically, the website had not undergone adequate load testing before launch. No one had simulated what would happen when millions of people tried to use it simultaneously. The contractors and government officials involved had ignored warning signs, had pushed ahead with the launch despite knowing that major problems remained unresolved, driven by political pressure to meet the deadline established by the Affordable Care Act itself. The result was a disaster that required months of emergency work by a new team of engineers brought in to essentially rebuild the website while it was running. The economic cost of healthcare.gov's failure is difficult to calculate precisely, but estimates suggest that fixing the website and dealing with the fallout cost around $2 billion. The political cost was equally severe. The botched launch gave ammunition to opponents of the Affordable Care Act, delayed enrollment for millions of Americans who needed health insurance, and became a symbol of government incompetence. It demonstrated that even with vast resources, even with years of preparation, even with the highest stakes, software projects can fail spectacularly if they are not properly managed, properly tested, and properly integrated. The healthcare.gov disaster was not caused by a single bug or a single line of bad code. It was a systemic failure of project management, quality assurance, and organizational coordination. In the realm of consumer technology, few failures have been as visible or as costly as Samsung's Galaxy Note 7 debacle. In August 2016, Samsung launched the Galaxy Note 7 smartphone to great fanfare. It was supposed to be the company's flagship device, packed with cutting-edge features. Instead, it became a literal fire hazard. Reports began surfacing of Note 7 devices overheating, catching fire, and exploding. Videos spread across social media showing phones bursting into flames, setting fire to cars, hotel rooms, and homes. Airlines banned the device from flights. Samsung initiated a recall, but even the replacement devices supposedly fixed continued to catch fire. Eventually, Samsung made the unprecedented decision to completely discontinue the Note 7, recalling every device worldwide and ceasing all production. The root cause was complex, involving both battery design flaws and software issues that failed to properly regulate charging and temperature. The software was supposed to prevent the battery from overheating, but it didn't account for certain edge cases in battery design. When batteries were slightly misshapen or had thin separators between positive and negative layers, the software's safety checks were insufficient to prevent thermal runaway. The economic impact on Samsung was staggering, estimated at over $5.3 billion in direct costs for the recall, lost sales, and damage control. The company's reputation took a severe hit, and competitors like Apple gained market share. The Note 7 disaster showed that software safety issues aren't limited to mission-critical systems like aircraft or medical devices. They can affect everyday consumer products, and when they do, the consequences can be immediate, visible, and dangerous. Consider also the vulnerability of our interconnected infrastructure to software failures. In February 2017, Amazon Web Services, the cloud computing platform that powers vast swathes of the internet, experienced a major outage in its S3 storage service. The cause was almost comically simple, and yet devastating in its impact. An engineer was debugging a problem and needed to take a small number of servers offline. He typed a command but made a typo, entering the wrong parameter. Instead of taking offline a few servers, the command took offline a massive number of servers, far more than the system could handle losing. The S3 service, which millions of websites and applications rely on for storage, went dark. Websites crashed. Mobile apps stopped working. Even AWS's own status page, which was supposed to tell customers about service disruptions, went down because it too relied on S3. The outage lasted for several hours and affected countless businesses. Slack, Quora, Trello, and thousands of other services that relied on AWS experienced downtime. The financial cost to affected businesses was estimated at between $150 and $160 million in lost productivity and revenue. The incident exposed a fundamental fragility in our cloud-dependent world. So many services and companies have outsourced their infrastructure to a handful of major cloud providers that when one of those providers has a problem, the ripple effects are enormous. The AWS outage wasn't caused by a sophisticated cyber attack or a complex technical failure. It was caused by a human error, a mistyped command, amplified by inadequate safeguards and recovery procedures. Amazon had not sufficiently tested its recovery process for such a large-scale disruption, so when it happened, it took much longer to fix than it should have. In the realm of social media, scale itself becomes a vulnerability. In March 2019, Facebook experienced one of the longest and most widespread outages in its history. Facebook's main site, along with Instagram and WhatsApp, were unavailable for over 14 hours, affecting billions of users worldwide. The cause was a server configuration change that had not been adequately tested. When the change was deployed, it triggered a cascade of failures across Facebook's infrastructure. The outage prevented people from communicating with friends and family, disrupted businesses that rely on Facebook for marketing and sales, and temporarily paralyzed a significant portion of the world's digital communication infrastructure. The estimated financial loss to Facebook itself was around $65 million in lost advertising revenue, but the broader economic impact, considering all the businesses and individuals affected, was far larger. These modern failures, from Boeing's deadly M-key system to Facebook's global outage, share a troubling characteristic. They occur in systems that have grown so large, so complex, so interconnected that no single person can fully understand how they work. The Boeing 737 MAX was not designed by one engineer, but by teams of engineers working on different subsystems. The healthcare.gov website was not built by one contractor, but by many contractors building different pieces. The AWS infrastructure is not managed by a single command center, but by countless systems coordinating with each other across data centers around the world. This complexity is both necessary and dangerous. It is necessary because modern systems need to do so many things, need to serve so many users, need to handle so many edge cases. But it is dangerous because complexity breeds emergent behaviors, unexpected interactions, failure modes that no one anticipated. The software industry has developed methodologies and practices meant to mitigate these risks. Code reviews, automated testing, continuous integration, staged rollouts, redundant systems, monitoring and alerting. But these safeguards are only as good as the people implementing them and the organizations supporting them. When deadlines are tight, when budgets are constrained, when competitive pressure is intense, the the temptation is always there to cut corners, to skip tests, to push code to production without fully verifying it. And sometimes those gambles work out fine. The code runs, the system stays up, the business moves forward. But sometimes the gamble fails and the consequences can be catastrophic. In the depths of night, when consciousness begins to blur and the boundaries between waking and dreaming grow thin, we might ask ourselves a question that feels both simple and profound. How did we arrive at this place, this moment in history where invisible code holds such power over our lives? The answer requires us to drift back through time, to understand how software evolved from a curiosity to a convenience, to an absolute necessity, how it spread through every corner of modern civilization like digital vines growing through the infrastructure of our world. In the early days of computing, software was simple enough that one person could understand an entire program. Code was measured in thousands of lines, not millions. Programs ran on single machines, not distributed across thousands of servers. When something went wrong, it was relatively straightforward to find and fix the problem. But as computers became more powerful and more ubiquitous, software grew in complexity to match. Operating systems went from managing simple input and output to coordinating millions of processes simultaneously. Business applications went from tracking inventory in a single warehouse to managing global supply chains spanning dozens of countries and thousands of suppliers. The internet connected these systems together, creating a web of dependencies where a failure in one place could cascade to failures everywhere else. This growth in complexity was not accidental. It was driven by insatiable demand for new features, better performance, greater convenience. Every new capability required more code, more systems, more integration. And as the complexity grew, so did the potential for failure. A program with 1,000 lines of code has relatively few places where bugs can hide. A program with 1,000,000 lines of code has essentially infinite places for things to go wrong. Modern software systems are not just complex, they are incomprehensibly complex. The Boeing 737 MAX's flight control software contains millions of lines of code. Windows operating system contains tens of millions of lines. A modern car has over 100 million lines of code distributed across dozens of embedded computers. No single person can hold all of that in their mind at once. We build these systems through specialization and abstraction, with different teams working on different pieces, trusting that when everything is assembled, it will work together properly. But trust is not the same as verification, and time and again, we see that the interfaces between different components, the assumptions that different teams make about how their pieces will interact with others, these are the places where failures lurk. The Mars Climate Orbiter crashed because one team assumed metric units, and another used imperial units. The Ariane 5 exploded because code from one rocket was reused in another, without checking that the assumptions built into that code still held true. The healthcare.gov website collapsed because different contractors built different pieces without adequate integration testing. The pattern repeats endlessly through the history of software failures. There is also the question of organizational culture and the incentives that drive decision-making. In a perfect world, software development would prioritize safety, quality, and reliability above all else. In the real world, software development is driven by deadlines, budgets, and competitive pressure. Companies want to get products to market faster than their rivals. Managers want to deliver projects under budget. Executives want to show profits to shareholders. These pressures create an environment where cutting corners becomes tempting, where thorough testing seems like an expensive luxury, where warnings from engineers about potential problems are dismissed as excessive caution or unnecessary pessimism. The Boeing 737 MAX disaster was fundamentally a failure of organizational culture. Boeing's management, facing intense competition from Airbus, made decisions that prioritized speed and cost savings over safety. They outsourced critical software development to low-paid contractors. They dismissed concerns raised by their own engineers. They withheld information about the MCAS system from pilots and regulators because revealing it would have required additional training, which would have made the MAX less attractive to airlines. At every decision point where safety and profit conflicted, profit won. The result was a system with inadequate safeguards, insufficient redundancy, and hidden complexity that pilots couldn't understand or control. When that system failed, hundreds of people died, and Boeing suffered damage to its reputation and finances that will take decades to repair. Knight Capital's $440 million loss in 45 minutes was similarly rooted in organizational failures. The company was under pressure to deploy new trading software quickly to participate in a new market program. In their haste, proper deployment procedures were not followed. Old code that should have been removed was left in place. The new code was not fully installed on all servers, and critically, there was no kill switch, no emergency brake that could immediately halt all trading if something went wrong. When the disaster unfolded, engineers scrambled to understand what was happening, but the system was designed to trade at high speed, and it did exactly that, executing millions of transactions before anyone could stop it. The company had optimized for speed and efficiency, but had not built in safeguards for catastrophic failure. These stories illuminate a paradox at the heart of modern software development. We are simultaneously getting better and worse at building reliable systems. Better because we have more tools, more methodologies, more accumulated knowledge about what works and what doesn't. Worse because the systems we are building are growing in complexity faster than our ability to manage that complexity. We can test individual components thoroughly, but we cannot test every possible interaction between components, every possible sequence of events, every edge case that might occur in production. The space of possible behaviors grows exponentially with system complexity, and at some point, comprehensive testing becomes mathematically impossible. This fundamental limitation means that all sufficiently complex software systems contain bugs. Not might contain bugs, but definitely contain bugs. Bugs that have not yet been discovered, that are lurking in some rarely executed code path, waiting for the right conditions to manifest. When a system is not mission critical, when a bug causes inconvenience rather than catastrophe, we tolerate this imperfection. Your web browser crashes occasionally, and you restart it. Your phone app glitches, and you close it and reopen it. These are annoyances, not disasters. But when software controls aircraft, medical devices, financial systems, power grids, nuclear reactors, the same fundamental limitation applies. These systems also contain undiscovered bugs, and sometimes those bugs kill people or destroy billions of dollars of value. The Theric 25 radiation therapy machine had a race condition bug that killed multiple people before it was discovered and fixed. But here is the truly disturbing part. That same bug existed in the earlier Theric 20 model. It was there all along, lurking in the code. The only reason it never killed anyone in the Theric 20 was that the Theric 20 had hardware interlocks that prevented the bug from causing harm. The software was already flawed, but the hardware saved it. When Boeing built the Therac 25 and removed those hardware interlocks, believing that software alone could ensure safety, they created the conditions for the latent bug to become lethal. This is one of the most important lessons from the history of software failures. Redundancy and defense in depth are essential. Systems should not rely on a single layer of protection, because that layer might have flaws you haven't discovered yet. Modern safety-critical systems are built with this principle in mind. Aircraft have multiple redundant computers running different software developed by different teams. If one computer fails or produces incorrect output, others can detect the problem and override it. Nuclear power plants have multiple independent safety systems, any one of which can shut down the reactor if something goes wrong. But redundancy is expensive, and it adds complexity, and there is always pressure to reduce costs and simplify systems. The Boeing 737 MAX's MKS system relied on a single angle of attack sensor with no redundancy, a design choice that saved money and reduced complexity, but created a single point of failure. When that sensor malfunctioned, there was no backup, no second opinion, no way for the system to recognize that its input data was wrong. The economic impact of software failures extends far beyond the direct costs of the incidents themselves. There are the obvious costs, the money lost by Knight Capital, the cost of recalling all the Note 7 devices, the expenses of fixing healthcare.gov, the compensation paid to victims of the 737 MAX crashes. But there are also indirect costs that are harder to measure but equally real. There is the damage to reputation and trust. Boeing was once regarded as the gold standard of aviation safety. That reputation, built over decades, was shattered by the MAX crashes. Rebuilding it will take years and countless resources. There is the cost of increased regulation that follows major failures. After the MAX crashes, aviation regulators around the world scrutinized Boeing's certification process more closely, adding time and expense to all future aircraft development. There is the cost of opportunity lost. While engineers are fixing bugs and dealing with failures, they are not working on new features and innovations. While executives are managing crises and testifying before Congress, they are not building the business. And there is the broader societal cost of reduced trust in technology itself. Every time a self-driving car crashes, every time a medical device malfunctions, every time a major website goes down, people's faith in our technological systems erodes a little bit more. This erosion of trust has real consequences for the adoption of new technologies and the willingness of people to rely on automated systems. A study commissioned by the National Institute of Standards and Technology in 2002 estimated that software bugs cost the United States economy approximately $60 billion annually. More recent estimates are far higher, with some analyses suggesting that poor software quality cost the US economy $2.41 trillion in 2022 alone. This staggering figure includes the costs of failed projects, operational failures, security breaches, and the ongoing expense of maintaining and patching flawed software. It represents roughly 10% of GDP, a massive hidden tax on our economy, caused by our collective inability to build reliable software at scale. These numbers are almost too large to comprehend, so let us ground them in specific examples. The global cost of preparing for the Y2K bug exceeded $300 billion. The Boeing 737 MAX groundings and related costs exceeded $20 billion. The 2017 Equifax data breach, which exposed sensitive personal information of 147 million people due to a software vulnerability that had not been patched, cost the company over $1.4 billion in settlements and remediation. The 2020 SolarWinds cyber attack, which compromised government agencies and major corporations through malicious code inserted into a software update, has ongoing costs that are still being calculated but are estimated in the tens of billions when considering all affected organizations. The COVID-19 pandemic accelerated digital transformation across every industry, which means we're now more dependent on software than ever before, which means the potential impact of software failures is greater than ever before. As we drift deeper into this history of failures, patterns begin to emerge from the darkness like constellations slowly revealed to adjusting eyes. These are not random accidents, not cosmic bad luck, but predictable consequences of how we build software, how we organize teams, how we respond to pressure and constraints. If we listen carefully to these stories, they whisper secrets about the nature of complexity, about the limits of human understanding, about the price we pay for the conveniences we have come to take for granted. Let us consider another dimension of software failure, one that plays out not in dramatic explosions or sudden crashes, but in slow erosion, in systems that gradually become unmaintainable, in technical debt that compounds like financial debt until the entire structure collapses under its own weight. Technical debt is the accumulated cost of shortcuts taken during development, of code written quickly without proper documentation, of patches applied to legacy systems without refactoring the underlying architecture. It is invisible to users, invisible to managers, invisible to everyone except the engineers who have to work with the code. But like termites eating away at the foundation of a house, technical debt slowly destroys the integrity of software systems until one day something breaks in a way that cannot be easily fixed. The story of the Pentium 50V bug in 1994 illustrates how even a small flaw can have outsized economic impact once it becomes public knowledge. Intel's Pentium processor had an error in its floating point division algorithm, a tiny flaw in the lookup table used for calculations. The bug was so rare that it would only cause an incorrect result approximately once every 360 billion division operations. For almost all users, the bug would never manifest in their entire lifetime of computer use. A mathematician named Thomas Nicely discovered the error and reported it to Intel. Intel's initial response was to offer replacement chips only to users who could demonstrate that they were actually affected by the bug. This dismissive approach proved to be a catastrophic public relations mistake. When news of the bug reached the media, it triggered something approaching mass hysteria. The technical reality of the bug, that it was extraordinarily rare and would not affect the vast majority of users, was overwhelmed by public perception and fear. Millions of people demanded replacement chips. Intel, facing a public relations nightmare and pressure from major computer manufacturers, eventually offered to replace any Pentium chip for any customer who wanted a replacement, no questions asked. The cost of this recall exceeded $475 million, nearly 5 times Intel's revenue for that quarter. The Pentium FDIV bug cost Intel hundreds of millions of dollars, not because the bug itself caused significant harm, but because the public perception and the company's handling of the issue spiraled out of control. This incident reveals an important truth about software failures in the age of instant communication and social media. The actual severity of a bug is sometimes less important than how it is perceived and how the company responds. A minor flaw that is handled poorly can become a major crisis. Conversely, a serious problem that is addressed quickly and transparently can sometimes be contained before it causes lasting damage. Intel learned this lesson the hard way, and the company's approach to handling subsequent issues became more proactive and customer-focused as a result. The realm of cryptocurrency and blockchain technology has produced its own spectacular software failures, demonstrating that even supposedly secure and decentralized systems are vulnerable to bugs and exploits. Mt. Gox, once the largest Bitcoin exchange in the world, handling over 70% of all Bitcoin transactions at its peak, collapsed in 2014 after losing approximately 850,000 bitcoins, worth roughly $450 million at the time. The company initially claimed the loss was due to a software glitch that created transactions that could never be fully redeemed. Later investigations revealed a more complex picture involving both technical failures and possible theft. About 200,000 bitcoins were eventually recovered, but the exchange declared bankruptcy and most customers lost their funds. The Mt. Gox disaster shook confidence in Bitcoin and cryptocurrency generally, demonstrating that these supposedly revolutionary technologies were vulnerable to the same kinds of failures as traditional systems. The technical flaw that Mt. Gox initially blamed, transaction malleability, was a known issue in the Bitcoin protocol that allowed attackers to modify transaction IDs, potentially confusing exchanges about whether transactions had actually been processed. But the deeper problem was Mt. Gox's poor security practices, inadequate monitoring, and failure to properly account for its Bitcoin holdings. The exchange was handling hundreds of millions of dollars worth of cryptocurrency, but it was run like a hobby project, without proper financial controls or security measures. When things went wrong, there was no safety net, no insurance, no regulatory oversight to protect customers. The cryptocurrency space has seen numerous other software-related disasters. The DAO hack in 2016 resulted in the theft of $50 million worth of Ethereum due to a vulnerability in smart contract code. The parity wallet bug in 2017 permanently froze over 500,000 Ethereum tokens, worth roughly $150 million at the time, due to a coding error that made the funds inaccessible forever. These incidents highlight the unique challenges of blockchain-based systems. Unlike traditional software, where bugs can often be fixed by deploying an update, smart contracts running on a blockchain are immutable once deployed. If they contain a bug, that bug cannot be patched without controversial hard forks or other extreme measures. The code is literally the law in these systems, which means that coding errors can have permanent, irreversible consequences. The gaming industry has also experienced high-profile software failures with massive economic impact. The launch of Cyberpunk 2077 in December 2020 became notorious as one of the most disastrous releases in gaming history. CD Projekt Red, the game's developer, had built enormous hype over years of development, promising a revolutionary open-world experience. When the game finally launched, it was riddled with bugs, performance problems, and missing features, particularly on older PlayStation and Xbox consoles. The game would crash frequently, characters would glitch through walls, textures would fail to load, and major systems were broken or incomplete. The backlash was swift and severe. Sony took the extraordinary step of removing Cyberpunk 2077 from the PlayStation Store and offering full refunds to all customers. Microsoft offered refunds as well. CD Projekt Red's stock price plummeted, losing billions in market value. The company was forced to issue public apologies, commit to months of patching and updates, and offer refunds to anyone who wanted one. The total cost to CD Projekt Red, including development costs, refunds, lost sales, and market value decline, exceeded $50 million in immediate impact, with longer-term damage to the company's reputation that will affect future releases. The Cyberpunk 2077 disaster was caused by a combination of factors: ambitious scope that exceeded the team's ability to deliver, management pressure to release the game before it was ready, insufficient testing on console platforms, and technical debt accumulated over years of development. The game had been delayed multiple times, but even with those delays, it launched in an unacceptable state. The lesson here is that deadlines, even self-imposed ones, can create pressure that leads to shipping broken software. The cost of delay seemed high to CD Projekt Red's management, but it turned out to be far lower than the cost of releasing a broken product. These modern failures in cryptocurrency and gaming might seem less critical than failures in aviation or medical devices, and in one sense that is true. No one died because of Mt. Gox's collapse or Cyberpunk 2077's bugs, but these incidents still affected millions of people and destroyed billions of dollars in value. They demonstrate that software failure is not confined to any one domain. Whether the software is controlling an aircraft or managing a cryptocurrency exchange or rendering a video game, the fundamental challenges are similar: complexity, time pressure, human error, inadequate testing, organizational dysfunction. The specific manifestations differ, but the underlying causes repeat across industries and decades. Let us turn our attention now to government and military systems, where software failures can have national security implications. The Patriot missile system, designed to intercept incoming missiles, suffered from a software bug that contributed to the death of 28 American soldiers in 1991 during the Gulf War. The system used an internal clock to track time, but due to a rounding error in the software that converted the time to a decimal fraction, the clock would gradually drift. For every hour the system ran, the clock would drift by about 0.34 seconds. This might seem insignificant, but at missile velocities, even a fraction of a second of error translates to hundreds of meters of position error. The Patriot battery that failed to intercept the Iraqi Scud missile that killed the 28 soldiers had been running for 100 hours, causing the clock to drift by 34 seconds, resulting in a position error of over 600 meters. The Scud missile passed outside the Patriot's search range and was not intercepted. This tragedy illustrates the importance of understanding how software behaves over time, not just at the moment it's deployed. The Patriot system's rounding error was small enough to be negligible in short operations, but it accumulated over time into a fatal flaw. The software had been tested, but apparently not tested for extended operations over many hours. This is a common failure mode in real-time systems. Rounding errors, memory leaks, buffer overflows, these problems can build up slowly and only manifest after the system has been running for a long time. By that point, the system is in production, lives may depend on it, and the consequences of failure can be catastrophic. In the realm of space exploration, software failures have ended missions, destroyed spacecraft, and cost billions of dollars. Beyond the Mars Climate Orbiter we discussed earlier, there have been numerous other examples. The Mariner 1 spacecraft, intended to fly by Venus in 1962, had to be destroyed shortly after launch due to a software bug. The guidance software was missing a single hyphen in the code, causing the rocket to veer off course. The loss cost approximately $18 million at the time, equivalent to over $150 million in today's money. The Mars Polar Lander, which crashed on Mars in 1999, likely failed due to a software bug that caused the spacecraft to prematurely shut down its descent engines. The loss cost approximately $165 million. The European Space Agency's Schiaparelli lander crashed on Mars in 2016 due to a software error in the inertial measurement unit, costing the mission hundreds of millions of dollars. Space missions are particularly vulnerable to software errors because there is no opportunity to physically access the spacecraft once it has launched. Any bugs in the software must be either fixed remotely through software updates, or they will cause the mission to fail. The stakes are extraordinarily high because of the immense cost of developing and launching spacecraft. A single software bug can destroy years of work and hundreds of millions of dollars of investment in seconds. Space agencies have developed rigorous software development and testing processes to minimize these risks. But the complexity of spacecraft systems and the harsh environments they operate in mean that failures still occur. In the quiet hours of contemplation, we might ask what these failures teach us about the future. We are building systems of ever-increasing complexity, incorporating artificial intelligence and machine learning algorithms whose decision-making processes are opaque even to their creators. We are connecting every device, every sensor, every piece of infrastructure into vast networks that span the globe. We're automating decisions that used to require human judgment, from trading stocks to driving cars to diagnosing diseases. And we are doing all of this at a pace that often outstrips our ability to fully understand the implications and adequately test for failures. The rise of artificial intelligence introduces new categories of software failure that we're only beginning to grapple with. Traditional software fails when it has bugs, when the code does not do what the programmer intended. But AI systems can fail even when they are working exactly as designed, because they make decisions based on patterns learned from data, and those patterns may not always be correct or appropriate. An AI system trained on biased data will make biased decisions. An AI system optimized for one metric may find unexpected and harmful ways to maximize that metric. An AI system making predictions based on correlations it has learned may fail catastrophically when the underlying relationships in the data change. There have already been notable AI failures with real-world impact. In 2018, Uber's self-driving car struck and killed a pedestrian in Arizona, the first recorded death caused by an autonomous vehicle. Investigation revealed that the car's sensors had detected the pedestrian 6 seconds before impact, but the software had difficulty classifying what it was seeing. Was it a car, a pedestrian, a bicycle? The system kept changing its classification, and by the time it definitively identified the pedestrian and decided to brake, it was too late. The human safety driver, who was supposed to be monitoring the system, was distracted and looking at her phone. This tragedy illustrates the challenge of AI safety. The system was not broken in a traditional sense. The sensors worked, the algorithms ran, but the software failed to make the right decision at the right time, and a person died. Amazon's hiring AI, which was supposed to help review job applicants, had to be scrapped after it was discovered that the system was systematically discriminating against women. The AI had been trained on historical hiring data, which reflected the tech industry's gender imbalance. The system learned to prefer male candidates because that pattern was in the training data. When Amazon engineers realized what was happening and tried to fix it by removing explicitly gendered terms, the AI found other proxy signals to continue the discrimination. This example illustrates a fundamental challenge with AI systems. They learn patterns from data, and if the data contains biases, the AI will learn those biases. And even when you try to remove the bias, the system may find subtle ways to recreate it. These AI failures are different in character from traditional software bugs, but they share a common thread with all the failures we have discussed. They arise from the gap between what designers intend and what the system actually does, from complexity that exceeds human ability to fully anticipate all possible behaviors, from pressure to deploy systems before they are adequately tested and understood. As AI becomes more prevalent in critical decision-making roles, from loan approvals to medical diagnosis to criminal sentencing, the potential for AI failures to cause harm at scale grows exponentially. Consider the financial sector, where algorithmic trading has become dominant. The Knight Capital disaster we discussed earlier was just one example of how automated trading systems can fail catastrophically. The 2010 flash crash provides another cautionary tale. On May 6, 2010, at 2:32 p.m., the Dow Jones Industrial Average began to plummet. Within minutes, it had dropped nearly 1,000 points, nearly 9% of its value, erasing roughly $1 trillion in market value. Individual stocks experienced bizarre price movements. Accenture briefly traded at 1 penny per share. Apple stock momentarily spiked to over $100,000 per share. Then, just as suddenly, the market began to recover. By 3:02 p.m., most of the losses had been reversed. The entire event lasted about 36 minutes, but it shook confidence in the stability of financial markets and raised serious questions about the risks of high-frequency algorithmic trading. The investigation into the flash crash revealed a complex chain of events. A large mutual fund executed a massive sell order using an automated algorithm. The algorithm was supposed to sell gradually, matching the volume of trading in the market. But the algorithm did not account for the fact that much of the trading volume it was matching against was other algorithms, creating a feedback loop. High-frequency trading firms bought and sold the same shares back and forth among themselves, creating artificial volume. The mutual fund's algorithm interpreted this as genuine market activity and accelerated its selling. This created more volatility, which caused other algorithms to withdraw from the market or switch to selling, which created even more volatility. The cascade happened faster than any human could track or intervene. Circuit breakers eventually kicked in, halting trading in some stocks and allowing the market to stabilize. But for those 36 minutes, the machines were in control, and they nearly tore the market apart. The flash crash demonstrated that interconnected automated systems can create emergent behaviors that no one predicted or intended. Each individual trading algorithm might be perfectly rational and well-designed, but when hundreds of algorithms interact with each other at high speed, the collective behavior can become chaotic and dangerous. This is a pattern we see repeatedly in complex systems. The individual components work fine in isolation, but the interactions between components create unexpected failure modes. The engineers who designed each trading algorithm could not have predicted how it would interact with every other trading algorithm in the market. The system as a whole had properties that emerged from the interactions, properties that could not be understood by examining any single component. Banking and financial institutions have also experienced massive software failures with far-reaching consequences. In 2018, TSB Bank in the United Kingdom attempted to migrate its customer data from its parent company's IT systems to a new independent platform. The migration was supposed to happen over a weekend with minimal disruption to customers. Instead, it became one of the most disastrous IT failures in banking history. When customers tried to access their accounts on Monday morning, many found they could not log in. Others logged in to find incorrect balances or could see other customers' account information. Payments failed to process. Direct debits were not honored. Customers were locked out of their own money for days or weeks. The chaos continued for months as TSB struggled to fix the problems and restore normal service. The CEO eventually resigned. The total cost to TSB exceeded £370 million, roughly $500 million in compensation to customers, additional IT spending, regulatory fines, and lost business. The TSB disaster was caused by a combination of factors. The new IT platform had not been adequately tested with realistic data volumes. The migration process itself was more complex than anticipated. And critically, when problems emerged, TSB did not have adequate fallback plans to revert to the old system or operate in a degraded mode. The bank was committed to the migration and pushed forward even as it became clear that things were going badly wrong. This pattern of escalating commitment, of refusing to back down or admit failure even when problems mount, appears in many software disasters. Organizations invest so much time, money, and reputation in a project that turning back seems more costly than pushing forward, even when pushing forward leads to catastrophe. In the healthcare sector beyond the Therac 25, software failures continue to affect patient care and safety. In 2018, the UK's National Health Service faced a crisis when a software error in a cervical cancer screening program resulted in approximately 450,000 women not being invited for their routine screenings. Some women who should have been screened developed advanced cervical cancer that might have been detected earlier. The error was traced to a software algorithm that incorrectly determined which women were due for screening. The cost in human terms, lives potentially lost or damaged, cannot be fully calculated. The financial and organisational cost to the NHS and the legal claims from affected patients continue to accumulate. Medical device software remains a persistent source of concern. In 2019, the Food and Drug Administration in the United States issued warnings about cybersecurity vulnerabilities in multiple medical devices, including pacemakers and insulin pumps. These devices run software, and that software can potentially be hacked or can malfunction. A pacemaker with a software bug could deliver incorrect electrical impulses to the heart. An insulin pump with compromised software could deliver wrong doses of insulin. As medical devices become more sophisticated and more connected, they become more dependent on software and therefore more vulnerable to software failures. The automotive industry has experienced its share of software-related recalls and failures. As cars have become increasingly computerized, with millions of lines of code controlling everything from engine management to entertainment systems, software bugs have become a major source of recalls. In 2015, Fiat Chrysler recalled 1.4 million vehicles due to a software vulnerability that allowed hackers to remotely take control of a Jeep Cherokee's steering, brakes, and transmission. Security researchers had demonstrated the exploit, showing they could disable a vehicle driving at high speed on a highway. The recall cost Fiat Chrysler over $1 billion and raised serious concerns about the cybersecurity of connected vehicles. This was not a bug in the traditional sense, but a design flaw that created a vulnerability. The software worked as designed, but the design itself was insecure. Toyota has issued multiple recalls related to software problems in its vehicles. In 2014, Toyota recalled 1.9 million Prius hybrid vehicles due to a software bug that could cause the vehicle to suddenly slow down or stop. In 2018, Toyota recalled 2.4 million hybrid vehicles due to a software problem with the engine control system. Each major recall cost hundreds of millions of dollars in repairs, customer compensation, and damage to reputation. The automotive industry is now grappling with the challenges of maintaining software quality and security across vehicle lifetimes that can span 10 to 20 years. A car sold in 2025 will still be on the road in 2040, potentially running software that is decades old, and may contain vulnerabilities or bugs that have not yet been discovered. The telecommunications industry has experienced catastrophic software failures that disrupted communications for millions of people. In 1990, AT&T's long-distance telephone network suffered a massive outage that disrupted service for 9 hours, affecting 75 million phone calls and 200,000 customers. The cause was a software bug in the system that managed switching between different network nodes. When one switch failed and then recovered, it sent a message to other switches. A bug in the software caused those switches to also crash and reboot. As each switch came back online, it triggered more crashes in a cascading failure that swept through the entire network. The economic cost of the outage was estimated at over $60 million, but the broader impact on businesses and individuals who could not make or receive calls was far larger. More recently, in 2020, CenturyLink, a major internet service provider, experienced a nationwide outage due to a software error in its network management systems. The outage lasted over 24 hours and disrupted internet service, 911 emergency services, and various business operations across the United States. When a network management card failed in one location, the system attempted to reroute traffic, but a software bug caused the rerouting to fail in a way that cascaded through the network. The company faced regulatory scrutiny and customer compensation costs, and the incident highlighted the vulnerability of critical infrastructure to software failures. The energy sector has also seen significant software-related incidents. In 2003, a software bug in the alarm system at FirstEnergy Corporation contributed to the Northeast blackout, one of the largest power outages in North American history. The blackout affected 50 million people across 8 US states and parts of Canada, lasted up to 4 days in some areas, and caused an estimated $6 billion in economic losses. The alarm system was supposed to alert operators when power lines were sagging or overloaded, but a race condition bug caused the alarms to fail silently. Operators did not realize that problems were developing in the grid until it was too late. Overloaded power lines sagged into trees, triggering cascading failures as the grid attempted to reroute power through other lines that then became overloaded themselves. The blackout was caused by multiple factors, but the software failure in the alarm system was a critical element that prevented operators from responding to the crisis before it spiraled out of control. In the realm of defense and national security, software failures can have implications that extend beyond economics into geopolitical consequences. In 1995, a Russian early warning system detected what appeared to be a submarine-launched ballistic missile heading toward Moscow. The Russian military went on high alert, and the nuclear briefcase was activated and brought to President Boris Yeltsin. For several tense minutes, Russia was closer to launching a nuclear retaliation than at any time since the Cuban Missile Crisis. Fortunately, Yeltsin and his military advisors decided to wait and see rather than launch an immediate counterstrike. It turned out that the Russian radar had detected a Norwegian scientific research rocket, and the software system had incorrectly classified it as an incoming missile. This near disaster was caused by a combination of factors, including inadequate information sharing between countries about planned rocket launches, but the software system's inability to correctly classify the radar signature played a central role. As we drift deeper into the quiet hours, surrounded by the gentle hum of machines that never truly sleep, we begin to see that these failures are not merely technical problems. They are reflections of human nature itself, of our ambition and impatience, our confidence and hubris, our desire to move fast and our reluctance to slow down and verify. The software we build is an extension of ourselves, and it inherits our virtues and our flaws. When software fails, it is usually because somewhere in the chain of decisions that led to its creation, a human made a choice that prioritized speed over safety, cost over quality, optimism over caution. The history of software failures is also a history of warnings ignored. In almost every major disaster we have discussed, there were warning signs before the catastrophic failure occurred. Engineers raised concerns about the Theric 25's lack of hardware interlocks, but those concerns were dismissed. Pilots reported problems with the 737 MAX's handling characteristics before the crashes, but those reports were not adequately investigated. The healthcare.gov website showed problems in testing that were known before launch, but the political pressure to meet the deadline overrode technical caution. Knight Capital had experienced smaller glitches in their trading systems before the massive failure, but the underlying issues were not addressed. Time and again, we see that the information needed to prevent disaster was available, but it was not acted upon because acting on it would have been inconvenient, expensive, or embarrassing. This pattern points to a fundamental tension in software development and deployment. There is always pressure to deliver faster, to cut costs, to meet deadlines, to beat competitors to market. These pressures are real and legitimate. Businesses need to be competitive. Projects have budgets. Customers have expectations. But safety and quality take time and resources. Thorough testing is expensive. Addressing every potential concern can delay launches. Building in redundancy and fail-safes adds complexity and cost. The temptation is always there to convince yourself that the risks are acceptable, that the shortcuts won't matter, that you'll fix problems later if they arise. And most of the time, you get away with it. Most software ships with bugs, and most of those bugs never cause serious harm. But occasionally the gamble fails, and the consequences can be devastating. Consider the evolution of software development methodologies over the past decades. In the early days of computing, software was developed using what we now call the waterfall model. Requirements were carefully specified, designs were thoroughly documented, code was written and tested extensively before deployment. This approach was slow and expensive, but it produced relatively reliable software for its time. As computing became more mainstream and competitive pressure increased, faster development methodologies emerged. Agile development, continuous integration, rapid iteration. These approaches allow companies to release software more quickly and respond to user feedback. They have enabled the rapid innovation we see in the tech industry, but they also create risks. When you are deploying new code to production every day, or even multiple times per day, when you are building features rapidly based on minimal specifications, when you're treating users as beta testers, the potential for bugs to slip through and cause problems increases. The rise of open-source software adds another dimension to this complexity. Modern applications are built on top of layers and layers of open-source libraries and frameworks. A typical web application might incorporate hundreds of different open-source components, each maintained by different developers or teams around the world. This ecosystem has been enormously beneficial, allowing developers to build sophisticated applications without reinventing every component from scratch. But it also creates dependency chains where a bug in one obscure library can affect thousands of applications that depend on it. In 2021, a critical vulnerability was discovered in Log4j, a widely used Java logging library. The vulnerability, known as Log4Shell, affected millions of applications and systems worldwide, from cloud services to enterprise software to consumer products. Organizations scrambled to patch their systems, and the incident highlighted how a single flaw in a widely used open-source component can create systemic risk across the entire software ecosystem. The growing complexity of software supply chains has made it increasingly difficult to understand all the dependencies and potential vulnerabilities in a system. When you use an open-source library, you are trusting not just that library but all of its dependencies as well, and you are trusting that the maintainers of those libraries will continue to update them, patch security vulnerabilities, and maintain compatibility. But open-source maintainers are often volunteers, working in their spare time without compensation. Burnout is common. Projects can be abandoned, and even well-maintained projects can contain subtle bugs that go undetected for years because no one has encountered the specific conditions that trigger them. The concept of technical debt, which we touched on earlier, deserves deeper exploration. Technical debt is the idea that shortcuts taken during development create future costs that must eventually be paid. If you write code quickly without proper documentation, you create debt because future developers will struggle to understand and maintain that code. If you build a system without adequate testing, you create debt because bugs will need to be fixed later. If you delay refactoring and optimization, you create debt because the system becomes harder to modify and extend. Like financial debt, technical debt accrues interest over time. The longer you wait to address it, the more expensive it becomes to fix. And like financial debt, technical debt can accumulate to the point where it becomes unsustainable, where the system becomes so fragile and unmaintainable that it must be completely rebuilt or abandoned. Many of the software failures we have discussed were at least partially caused by accumulated technical debt. The healthcare.gov website was built by multiple contractors working on different pieces, and the integration between those pieces was poor because no one had overall responsibility for the architecture. This is organizational technical debt, where the structure of the project creates problems that compound over time. The Boeing 737 MAX's MCAS system was layered on top of an existing aircraft design to compensate for aerodynamic changes, rather than redesigning the aircraft from scratch. This is architectural technical debt, where you work around fundamental design issues rather than addressing them properly. The Ariane 5 reused code from the Ariane 4 without fully verifying the assumptions built into that code. This is legacy technical debt, where old code is carried forward into new contexts where it may no longer be appropriate. The challenge with technical debt is that it is invisible to non-technical stakeholders. Managers and executives see features being delivered, products being shipped, customers being served. They do not see the growing fragility beneath the surface, the accumulating complexity, the increasing difficulty of making changes without breaking something. Engineers understand that the system is becoming harder to work with, that changes that should be simple are taking longer, that the number of bugs is increasing. But communicating this to decision makers is difficult because technical debt cannot be easily quantified or demonstrated. It is a gradual erosion rather than a sudden crisis, at least until it reaches the point where the system fails catastrophically. Let us turn our attention now to the regulatory and legal implications of software failures. When software kills people or causes massive economic damage, questions of liability and accountability arise. Who is responsible when an autonomous vehicle crashes? The software developer who wrote the code, the company that manufactured the vehicle, the person who was supposed to be monitoring the system. When a medical device malfunctions and harms a patient, who bears the liability? These questions are becoming increasingly important as software becomes more autonomous and more critical to safety. Traditional product liability law was developed for physical products that fail in predictable ways. Software fails in unpredictable ways, often due to rare combinations of circumstances that were not and could not have been fully tested. How should liability be assigned when a bug only manifests under specific conditions that occur once in 1 billion transactions? The Boeing 737 MAX crashes led to criminal charges against Boeing and individual executives, a relatively rare outcome for software-related failures. The Department of Justice concluded that Boeing had defrauded regulators by concealing information about the MCAS system. Boeing paid $2.5 billion in fines and compensation as part of a deferred prosecution agreement. This case may represent a turning point in how software failures are treated legally, particularly when they involve concealment of safety-critical information and result in loss of life. Other software failures have led to regulatory actions, fines, and lawsuits, but the legal framework for dealing with software liability remains evolving and inconsistent across jurisdictions. The European Union has been at the forefront of regulating software and digital systems, with regulations like the General Data Protection Regulation addressing data handling and privacy, and emerging regulations around AI systems attempting to establish safety and accountability standards. The challenge for regulators is that software evolves much faster than regulatory processes. By the time regulations are written and implemented, the technology has often moved on to new paradigms that the regulations did not anticipate. There is also the risk that overly restrictive regulations could stifle innovation, while overly permissive regulations could allow dangerous systems to be deployed. Finding the right balance is extraordinarily difficult, particularly when the technology itself is complex and not well understood even by experts. Insurance companies are grappling with how to assess and price the risks associated with software failures. Cyber insurance has become a significant market, covering losses from security breaches and cyber attacks. But insurance for software failures more broadly, for bugs and glitches that cause operational failures rather than security compromises, is less developed. The challenge is that software risks are difficult to assess. Traditional actuarial methods rely on historical data about failure rates and loss distributions, but software failures are often novel and unpredictable. A system that has run successfully for years can suddenly fail due to a latent bug triggered by specific conditions. And the potential losses from software failure can be enormous and highly variable, from minor inconveniences to billion-dollar disasters. This makes it difficult for insurers to price policies appropriately without either charging prohibitively high premiums or exposing themselves to catastrophic losses. The cybersecurity dimension of software failures has become increasingly prominent in recent years. Software vulnerabilities can be exploited by attackers to steal data, disrupt operations, or cause damage. The NotPetya attack in 2017, which was initially disguised as ransomware but was actually designed to cause maximum destruction, leveraged software vulnerabilities to spread rapidly through corporate networks. The attack caused an estimated $10 billion in damage worldwide, making it one of the most costly cyber incidents in history. Shipping company Maersk, pharmaceutical company Merck, and many other major corporations were severely impacted, with some losing entire networks that had to be rebuilt from scratch. The attack exploited vulnerabilities that were known and for which patches had been released, but many organizations had not applied the patches promptly. This is a common pattern in security breaches. The vulnerability is known and a fix is available, but organizations delay implementing the fix due to concerns about disrupting operations or compatibility issues, and that delay creates an opportunity for attackers. The WannaCry ransomware attack in 2017 similarly exploited a known vulnerability in Windows systems for which Microsoft had released a patch months earlier. The attack infected over 200,000 computers in 150 countries, disrupting hospitals, factories, and government agencies. The UK's National Health Service was particularly hard hit, with hospitals forced to cancel operations and turn away patients as their computer systems were locked by the ransomware. The estimated cost exceeded $4 billion globally. The attack highlighted the challenge of patch management at scale. Even when fixes are available, deploying them across large organizations with diverse systems and applications is complex and time-consuming. Some systems cannot be easily patched because they are running critical processes that cannot be. interrupted, or because the patches might break compatibility with other software. This creates a perpetual window of vulnerability where known flaws exist but remain unfixed. In these contemplative hours, as we trace the threads of failures through time, we arrive at a question that feels both urgent and profound. Are we building systems we can no longer control? The trajectory of software development over the past decades has been toward greater automation, greater interconnection, greater complexity. We have systems that trade stocks in microseconds, that drive cars, that diagnose diseases, that control power grids and air traffic and nuclear reactors. We have created a technological civilization whose critical functions are mediated by software that no single person fully understands. This is not hyperbole or fear-mongering. It is simply the mathematical reality of complexity. A modern car contains over 100 million lines of code. The Large Hadron Collider's control systems contain around 50 million lines. The Android operating system contains 12 to 15 million lines. No human being can hold that much code in their mind at once, can trace through all possible execution paths, can anticipate all possible interactions and failure modes. We manage this complexity through abstraction and modularity. We break systems into components that can be understood individually, and we trust that when those components are assembled correctly, the whole system will function as intended. This approach works remarkably well most of the time. But abstraction has limits. Complex systems have emergent properties that cannot be predicted by analyzing the components in isolation. The flash crash emerged from the interaction of many trading algorithms, each of which was individually reasonable. The Northeast blackout emerged from a cascade of power grid failures that began with a single line touching trees, but was exacerbated by a software bug in an alarm system. These emergent failures arise from the complexity of the system as a whole, not from flaws in individual components. The concept of brittleness versus resilience is central to understanding why some systems fail catastrophically, while others degrade gracefully. A brittle system is one that works perfectly under normal conditions, but fails completely when something goes wrong. The Boeing 737 MAX's MCAS system was brittle because it relied on a single sensor with no redundancy. When that sensor failed, the system had no way to recognize the failure and failed catastrophically. A resilient system is one that can continue to function, perhaps in a degraded mode, even when components fail. Resilient systems have redundancy. They have multiple ways to accomplish critical tasks. They have graceful degradation, where losing some functionality does not cause total failure. Building resilient systems is expensive and complex, but it is essential for safety-critical applications. The principle of defense in depth, borrowed from military strategy and cybersecurity, is crucial for building resilient systems. Defense in depth means having multiple layers of protection, so that if one layer fails, others are still in place. The Theric 25 violated this principle by removing hardware interlocks and relying solely on software for safety. When the software failed, there was no backup protection. Modern safety-critical systems are designed with defense in depth, multiple independent safety systems, hardware interlocks in addition to software checks, human oversight in addition to automated controls. But implementing defense in depth requires accepting additional cost and complexity, and there is always pressure to simplify, to eliminate redundancy, to trust that the primary system will work. The human factors in software failures deserve careful consideration. Many failures involve automation that exceeds human ability to understand or intervene. When the Boeing 737 MAX's MKS system activated, Pilots were fighting against an invisible force they did not understand. When Knight Capital's trading system went haywire, it executed millions of transactions faster than any human could comprehend or stop. When the flash crash unfolded, the market moved too quickly for human traders to keep pace. We have built systems that operate at speeds and scales that exceed human cognition, and when those systems fail, humans often cannot intervene effectively. This creates a dangerous dynamic where automation is in control during normal operations, but when something goes wrong, humans are suddenly expected to take over and fix problems they may not understand in systems operating faster than they can think. The concept of automation complacency is well studied in aviation and other domains. When automated systems work well most of the time, humans become complacent, trusting the automation and paying less attention. When the automation fails, humans are often caught off guard and their skills may have atrophied from lack of practice. The Uber self-driving car that killed a pedestrian had a human safety driver who was supposed to be monitoring the system, but she was distracted, looking at her phone because the car had been driving itself successfully and there seemed to be nothing for her to do. When the automation failed to properly identify the pedestrian, the human was not ready to intervene. This is a fundamental challenge with semi-autonomous systems. They lull humans into complacency during normal operations, but then demand instant expert intervention during emergencies. Software development culture and practices vary enormously across organizations and industries, and these variations have real consequences for software reliability. In some domains, like aerospace and medical devices, software development follows rigorous processes with extensive documentation, formal verification, and multiple levels of review and testing. In other domains, like consumer web applications and games, development is much more rapid and informal, with minimal documentation, and testing primarily done by users after release. These different approaches reflect different priorities and constraints. A medical device manufacturer cannot afford to release buggy software because the consequences could be fatal. A gaming company might release buggy software because the competition is fierce, and delaying release could mean losing market share, and bugs in games rarely cause serious harm. But as software spreads into more safety-critical domains, the informal development practices of consumer technology are sometimes applied in contexts where they are inappropriate. The Boeing 737 MAX scandal revealed that some flight control software was developed by low-paid contractors working under tight deadlines, using development practices more appropriate for a mobile app than for life-critical aircraft systems. This mismatch between development practices and the criticality of the application is a recurring theme in software failures. Organizations sometimes fail to recognize that the software they are building has life or death implications, and therefore requires different development practices than non-critical software. The economics of software quality present a difficult optimization problem. Improving software quality requires investment in testing, code reviews, formal verification, better development tools, more experienced engineers. These investments reduce the likelihood of bugs and failures, but they also increase development cost and time. For an individual company, the incentive calculation can favor cutting corners on quality, especially if the company does not expect to bear the full cost of failures. If failures are rare and their costs are distributed across many victims, rather than falling directly on the software developer, then investing heavily in quality may not make economic sense from the company's narrow perspective. But from a societal perspective, inadequate software quality imposes enormous costs, as we have seen. This is a classic externality problem, where the costs of failures are not fully borne by the parties making decisions about quality investment. Regulation, liability law, and industry standards can help align private incentives with social welfare by ensuring that companies bear more of the costs of their software failures. If software developers know they will face significant fines, lawsuits, and reputational damage when their software fails, they will invest more in quality. But as we discussed, the legal and regulatory framework for software is still evolving and varies widely across jurisdictions. In some cases, software is treated like a product subject to product liability law. In other cases, it is treated more like a service, with liability limited by contracts and terms of service. The lack of consistent legal standards creates uncertainty and may allow some software developers to avoid accountability for failures. The open source software ecosystem presents unique challenges for accountability and quality. When software is developed by volunteers and distributed for free, traditional notions of liability do not apply easily. If you use an open source library and it has a bug that causes your application to fail, you generally cannot sue the library's developer because you were not paying for the software and likely accepted a license that disclaims warranties and liability. This creates a potential tragedy of the commons, where critical infrastructure depends on open source components, maintained by volunteers who have no financial incentive to maintain quality and no liability if things go wrong. The Log4j vulnerability highlighted this risk. Log4j is maintained by a small group of volunteers as part of the Apache Software Foundation. When a critical vulnerability was discovered, those volunteers worked around the clock to develop and release patches, but they were not compensated for this emergency work, and they bore no legal liability for the vulnerability having existed in the first place. Some open source projects are supported by companies or foundations that provide funding and resources, but many are not. The infrastructure of the internet and modern software development depends on a vast ecosystem of open source components, many of which are maintained by individuals in their spare time. This is simultaneously one of the great strengths and great vulnerabilities of the modern software ecosystem. The strength is that open source allows rapid innovation and collaboration across organizational boundaries. The vulnerability is that critical systems depend on components whose maintenance and quality are not assured. As we drift further into this examination, we encounter the question of education and professional standards. Unlike many professions that involve public safety, software engineering has minimal licensing or certification requirements. Anyone can write software, and anyone can call themselves a software engineer. There are no mandatory educational requirements, no professional licensing exams, no regulatory boards that can revoke your right to practice if you act unethically or incompetently. This lack of professional standards has allowed the software industry to grow rapidly and has created opportunities for people from diverse backgrounds to enter the field. But it also means that there is enormous variation in the skills and practices of people writing software, including software for safety-critical applications. Some have called for software engineering to become a licensed profession, similar to civil engineering or architecture, with mandatory education, certification exams, and professional ethics standards. The argument is that as software becomes more critical to safety and security, we need mechanisms to ensure that people writing safety-critical software have adequate training and are held to professional standards. The counter-argument is that licensing would stifle innovation, create barriers to entry, and be difficult to implement in a rapidly evolving field where best practices are constantly changing. This debate remains unresolved, and different countries have taken different approaches. In some jurisdictions, certain types of safety-critical software must be developed by licensed professional engineers, while in others there are no such requirements. The role of software testing and quality assurance has evolved significantly over the decades. In the early days, testing was often an afterthought, done manually by dedicated testers after the software was written. Modern practices emphasize automated testing, continuous integration, and building quality in from the start rather than testing it in at the end. Test-driven development, where tests are written before the code, has become popular in some communities. Formal verification methods, which use mathematical techniques to prove that software meets its specifications, are used for the most critical systems. But all of these approaches have limitations. Automated tests only check what you tell them to check, and you may not think to test for edge cases that only occur under rare conditions. Formal verification is extremely expensive and time-consuming, and can only prove properties that are formally specified, which itself requires deep understanding of what the software should do. No amount of testing can prove the absence of all bugs in any reasonably complex software system. As night deepens and the world grows quieter still, we might reflect on the psychological and organizational factors that contribute to software failures. The culture within an organization profoundly affects the quality and reliability of the software it produces. In organizations where engineers feel empowered to raise concerns, where safety is genuinely prioritized over schedule, where there is a blameless post-mortem culture that treats failures as learning opportunities rather than occasions for punishment, software tends to be more reliable. In organizations where there is pressure to meet unrealistic deadlines, where raising concerns is seen as being negative or not a team player, where failures are met with finger-pointing and blame, the conditions are ripe for disasters. The Boeing 737 MAX disaster was as much an organizational failure as a technical one. Engineers who raised concerns about MCAS were overruled by management focused on competitive and financial considerations. The company's culture had shifted over the years from one dominated by engineers to one dominated by financial executives. Cost-cutting and schedule pressure took precedence over the engineering excellence that had once been Boeing's hallmark. This cultural shift created an environment where shortcuts seemed acceptable, where critical safety systems were inadequately designed, where information was withheld from regulators and customers. The crashes were the ultimate consequence of this cultural deterioration. The concept of normalization of deviance, identified by sociologist Diane Vaughan in her analysis of the Challenger space shuttle disaster, applies to many software failures as well. Normalization of deviance is the process by which unacceptable practices or standards gradually become acceptable through repetition. The first time you skip a test, you might feel uncomfortable about it. The 10th time, it feels normal. The 100th time, it is just how things are done. Over time, an organization can drift far from its stated standards and best practices through this gradual process, without anyone consciously deciding to lower standards. Each small deviation seems acceptable in isolation, but the cumulative effect is to create an organization where serious flaws are tolerated. The Knight Capital disaster involved normalized deviance. The practice of leaving old code in place rather than properly removing it had apparently become routine. The deployment process that failed to properly install new code on all servers must have been less rigorous than proper practice would require. These deviations from best practice probably did not cause problems most of the time, so they became normalized. Until the day when the combination of old code still being present and new code not being fully deployed created a catastrophic failure. Similarly, the Therac 25's race condition bug existed in earlier models, but had never caused harm because hardware interlocks prevented it. This may have led developers to become less concerned about software bugs, believing that the hardware would catch any problems. When the hardware interlocks were removed, the normalized deviance of accepting buggy software suddenly became lethal. Communication failures between teams and organizations are another recurring theme. The Mars Climate Orbiter crashed because one team was using imperial units and another was using metric units, and this interface specification was not properly verified. The Ariane 5 exploded because assumptions about the flight envelope were not properly communicated between the teams working on different components. The healthcare.gov website failed because different contractors were working on different pieces without adequate coordination and integration testing. In all of these cases, the information needed to prevent the failure existed somewhere within the organization or across organizations, but it was not effectively communicated to the right people at the right time. Large software projects involve many people and often multiple organizations, and the coordination challenges are immense. Each team may be working with different assumptions, different priorities, different technical approaches. Interface specifications can be ambiguous or incomplete. Changes made by one team can have unexpected effects on other teams' components. The larger and more distributed the project, the harder it becomes to maintain a coherent shared understanding of how everything fits together. This is why system integration is often where the most serious problems surface. Each component might work fine in isolation, but when they are brought together, the interactions create failures that were not anticipated. The phenomenon of software aging is less widely recognized but important. Software systems tend to degrade over time even if the code itself does not change. The environment in which the software runs evolves, operating systems are updated, hardware changes, network conditions shift, user behavior patterns change, data volumes grow. Software that worked well when it was first deployed may gradually become less reliable as the environment around it changes. Memory leaks, where software slowly consumes more and more memory until the system crashes, are a classic example of software aging. The leak might be tiny, but over days or weeks of operation, it accumulates until the system fails. The Patriot missile system's clock drift is another example. The rounding error was tiny per unit time, but it accumulated over hours until the error became large enough to cause the system to fail at its mission. Legacy systems, software that was written years or decades ago but is still in use, present particular challenges. Over time, the original developers may have moved on. Documentation may be lost or outdated. The programming languages or frameworks used may have fallen out of common use. Making changes to legacy systems is risky because the code is difficult to understand and there may be hidden dependencies and assumptions that are not documented. But not making changes is also risky because the system may no longer be adequate for current needs or may have security vulnerabilities that are not being patched. Many organizations struggle with aging legacy systems that are critical to their operations, but are increasingly difficult and expensive to maintain. The Y2K problem was fundamentally a legacy systems problem. Code written in the 1960s and 1970s was still running in the 1990s, and the assumptions built into that code about date representation were no longer valid. Fixing the problem required finding every place in millions of lines of code where dates were handled and updating the logic. This was expensive and time-consuming, but delaying was not an option because the calendar would roll over to 2000 whether the systems were ready or not. The fact that Y2K was ultimately handled without major disasters is a testament to the massive effort that went into remediation, but it also highlights the risks of long-lived systems where assumptions that were reasonable at the time of development become problematic decades later. The question of how to build software that will remain reliable and maintainable over decades is increasingly important as more of our critical infrastructure runs on software. A bridge or building designed today is expected to last 50 to 100 years. Software systems are increasingly similar in their expected lifespan, but the practices for ensuring long-term reliability are less mature. How do you write code today that will still be comprehensible and maintainable in 2050? How do you choose programming languages and frameworks that will still be supported 3 decades from now? How do you document assumptions and design decisions in a way that will be useful to maintainers who come along years later? These questions do not have simple answers, but they are becoming urgent as software infrastructure accumulates. The concept of software obsolescence is related but distinct from aging. Obsolescence occurs when the technology stack a system is built on is no longer supported or widely used. Windows XP systems, for example, became obsolete when Microsoft stopped providing security updates, but many organizations continued running them because the applications they needed only worked on XP. These obsolete systems are vulnerable to security threats and are difficult to maintain, but replacing them may be prohibitively expensive if it requires rewriting all the applications that depend on them. The healthcare sector has struggled with obsolete medical devices that run on ancient operating systems, but cannot be updated because the device manufacturers no longer support them, or because regulatory approval would be required for any changes. The economics of software maintenance are often poorly understood. When a software project is budgeted, the focus is usually on the initial development cost. But maintenance costs over the lifetime of the system typically far exceed the initial development cost. Estimates vary, but some studies suggest that 60 to 90% of the total cost of software occurs after the initial release, in maintenance, updates, bug fixes, and enhancements. Yet maintenance is often underfunded and undervalued. Maintenance work is less glamorous than building new features, and maintainers often struggle to get resources and recognition. This leads to a situation where systems are not adequately maintained, technical debt accumulates, and reliability degrades over time until the system becomes unmaintainable and must be replaced. The global nature of modern software development adds another layer of complexity. Software is increasingly developed by distributed teams spread across multiple countries and time zones. A company in the United States might have developers in India, Eastern Europe, and South America all working on the same code base. This distribution allows companies to access global talent and operate around the clock, but it also creates communication challenges. When teams are not co-located, informal communication becomes more difficult. Nuances can be lost in written communication or video calls. Time zone differences mean that getting quick answers to questions may require waiting hours for someone to wake up. Cultural differences in communication styles and work practices can lead to misunderstandings. The Boeing 737 MAX software development involved offshore contractors. An investigation suggested that communication and coordination challenges may have contributed to the problems. When critical safety systems are being developed by distributed teams with varying levels of expertise and different cultural approaches to raising concerns, the potential for miscommunication and oversights increases. This is not to say that distributed development is inherently risky, but it requires more deliberate attention to communication, coordination, and shared understanding than co-located development. The benefits of global talent access must be balanced against the costs of coordination across distance and culture. Artificial intelligence and machine learning are increasingly being incorporated into software systems, and this introduces new categories of potential failures. Traditional software is deterministic. Given the same inputs, it produces the same outputs. AI systems are probabilistic. Their outputs depend on patterns learned from training data and may vary even with identical inputs. This makes AI systems harder to test and verify. You cannot simply check whether the output is correct for a given input, because the notion of correct may be ambiguous. An AI system that diagnoses diseases based on medical images might be 95% accurate. But what about the 5% where it is wrong? How do you identify which cases it will fail on? The stillness of the late-night hours seems appropriate for contemplating these questions about the uncertain future we are building. Machine learning systems have already demonstrated failure modes that differ fundamentally from traditional software bugs. They can make predictions that are accurate on average but wildly wrong for specific cases. They can be adversarially manipulated, where small changes to inputs that are imperceptible to humans cause the AI to produce completely different outputs. They can exhibit biases learned from training data, discriminating against certain groups in ways that may violate ethical norms or laws. They can be brittle, working well within the distribution of their training data, but failing unpredictably on inputs that differ even slightly from what they were trained on. The autonomous vehicle that killed a pedestrian in Arizona is a stark example. The AI system was trained on vast amounts of data showing cars, pedestrians, bicycles, and other objects. It had successfully navigated thousands of miles without incident. But when confronted with a pedestrian walking a bicycle across the road at night, in a location where the AI did not expect to encounter pedestrians, the system failed to correctly classify what it was seeing, and failed to respond appropriately. This type of failure, where an AI system encounters something outside its training distribution and fails, is fundamentally different from a bug where code does not do what the programmer intended. The code was doing exactly what it was programmed to do, which was to make decisions based on learned patterns. The problem was that the learned patterns were inadequate for this specific situation. As AI systems are deployed in more critical roles, from medical diagnosis to loan approvals to hiring decisions to criminal justice, the potential for these failures to cause harm at scale grows. An AI system that denies loans to qualified applicants based on biased patterns in training data can perpetuate and amplify existing inequalities. An AI system that provides incorrect medical diagnoses can lead to wrong treatments and patient harm. And critically, these failures may be difficult to detect because AI systems are often opaque. Even the developers who created an AI system may not be able to fully explain why it makes specific decisions. This opacity makes it hard to debug problems, hard to verify correctness, and hard to hold anyone accountable when things go wrong. The question of AI alignment, ensuring that AI systems do what we actually want them to do, rather than finding unexpected ways to optimize whatever objective function they were given, is becoming increasingly important. There are already examples of AI systems finding loopholes or unexpected strategies to maximize their reward functions in ways that were not intended. An AI system trained to play a game might discover an exploit that allows it to score points without actually playing the game as intended. An AI system optimizing for engagement might promote inflammatory or misleading content because that generates more clicks. These are relatively benign examples, but as AI systems become more powerful and more autonomous, the potential for misalignment to cause serious harm increases. The integration of AI into software systems creates hybrid systems, where some components are traditional deterministic code and other components are probabilistic machine learning models. These hybrid systems can be particularly difficult to test and verify because they combine different failure modes. A bug in the traditional code can cause the AI component to receive incorrect inputs, or the AI component can produce outputs that trigger bugs in the traditional code. The interactions between deterministic and probabilistic components can create emergent behaviors that are difficult to predict or understand. This is uncharted territory in software engineering, and we are still developing methodologies and best practices for building reliable hybrid AI systems. Quantum computing, though still in early stages of development, represents another future paradigm shift that will bring new challenges for software reliability. Quantum computers operate on fundamentally different principles than classical computers, and quantum software must account for phenomena like superposition and entanglement that have no classical analogue. Quantum systems are also extraordinarily fragile, subject to decoherence and errors from environmental interactions. Quantum error correction is possible but requires substantial overhead. As quantum computing matures and begins to be used for practical applications, we will encounter new classes of software failures related to quantum phenomena. These failures may be even more subtle and difficult to understand than classical software bugs. The Internet of Things, connecting billions of devices from refrigerators to industrial sensors to medical implants, creates a vast attack surface and many opportunities for software failures to have real-world consequences. A bug in smart home software might lock you out of your house or disable your heating system. A bug in industrial control software might cause manufacturing equipment to malfunction or create safety hazards. A bug in a connected medical device might cause it to deliver incorrect treatments. The proliferation of connected devices means that software bugs that once would have been mere inconveniences can now have direct physical consequences. And because many IoT devices are inexpensive and mass-produced, they may not receive the same level of software quality assurance as more expensive systems. Security vulnerabilities in IoT devices are a particular concern because many devices are deployed in locations where they are not easily updated and may remain in service for many years. A security flaw in a smart thermostat installed in 2025 might still be exploitable in 2035 if the device is never updated. Botnets of compromised IoT devices have already been used to launch massive distributed denial of service attacks. The Mirai botnet in 2016 comprised hundreds of thousands of compromised IoT devices like cameras and routers, and was used to launch attacks that temporarily disabled major internet services. The economic damage from such attacks is difficult to quantify, but includes both the direct costs of the disruption and the broader costs of reduced trust in internet services. Cloud computing and the concentration of computing resources in large data centers operated by a handful of companies creates systemic risks. As we saw with the AWS S3 outage, when a major cloud provider experiences problems, the ripple effects can be enormous because so many services depend on that infrastructure. The convenience and cost-effectiveness of cloud computing have led many organizations to consolidate their IT infrastructure with cloud providers, but this consolidation creates single points of failure at a massive scale. A major outage at AWS, Microsoft Azure, or Google Cloud Platform can affect millions of websites and applications simultaneously. And if a software bug or cyber attack were to compromise one of these major cloud providers, the consequences could be catastrophic on a scale never before seen. The supply chain for software is increasingly complex and global, creating vulnerabilities that can be exploited. The SolarWinds attack demonstrated that malicious code inserted into a software update for a widely used network management tool could compromise thousands of government agencies and corporations. The attackers infiltrated SolarWinds' development environment and inserted malicious code into a legitimate software update. When customers installed the update, they unknowingly installed malware that gave the attackers access to their networks. This type of supply chain attack is particularly insidious because it subverts the trust relationship between software vendors and their customers. If you cannot trust software updates from legitimate vendors, how do you keep your system secure and up to date? The complexity and interconnectedness of modern software systems means that failures increasingly have cascading effects across organizational and national boundaries. A bug in one system can trigger failures in other systems that depend on it, which can trigger failures in still other systems, in a cascade that can be difficult to predict or control. The interconnected nature of financial markets means that a trading glitch at one firm can affect prices and trigger automated responses at other firms, as we saw in the flash crash. The interconnected nature of power grids means that a failure in one region can cascade to neighbouring regions, as we saw in the Northeast blackout. As systems become more tightly coupled and more interdependent, the potential for cascading failures increases. The concept of cyber-physical systems, where software directly controls physical processes, is expanding rapidly. Autonomous vehicles, industrial control systems, smart grids, and many other applications involve software making real-time decisions that have immediate physical consequences. Failures in cyber-physical systems can cause not just data loss or financial harm, but physical damage and loss of life. The Stuxnet worm, discovered in 2010, was a sophisticated piece of malware designed to sabotage Iran's nuclear enrichment program by causing centrifuges to malfunction. It demonstrated that software could be weaponized to cause physical destruction of industrial equipment. While Stuxnet was a deliberate attack rather than an accidental bug, it illustrates the principle that software controlling physical systems can cause physical harm. The increasing use of software in warfare and defense systems raises profound ethical and practical questions. Autonomous weapon systems that can select and engage targets without human intervention are being developed and deployed. These systems use AI to identify targets and make firing decisions in milliseconds. The promise is faster reaction times and reduced risk to friendly forces. The peril is that software bugs or AI failures in these systems could lead to incorrect target identification and unintended casualties. The decision to take a human life is perhaps the most consequential decision that can be made, and delegating it to software systems that may have bugs or limitations we do not fully understand is deeply troubling. International debates about the ethics and legality of autonomous weapons continue, but the technology is advancing faster than the policy and legal frameworks. The aggregate economic impact of software failures, as we've traced through this long contemplation, is truly staggering. From the hundreds of millions lost in individual incidents like Knight Capital and the Pentium bug, to the billions lost in major disasters like the Boeing 737 MAX and Y2K, to the trillions in cumulative costs estimated by industry studies, software failures represent a massive drag on the global economy. And these are only the costs we can measure. The opportunity costs, the innovations that did not happen because resources were diverted to fixing failures, the economic activities that did not occur because systems were down, the trust that was lost. These indirect costs are harder to quantify but equally real. Yet despite this history of failures and the enormous costs they have imposed, we continue to build ever more complex systems, to automate ever more critical functions, to increase our dependence on software. This is not irresponsible or irrational. Software, despite its flaws, has enabled enormous improvements in productivity, connectivity, healthcare, safety, and quality of life. The benefits of software far outweigh the costs of failures, at least in aggregate. But this does not mean we should be complacent. Every failure is an opportunity to learn, to improve our practices, to build more reliable systems. The question is whether we are learning fast enough, whether the rate of improvement in software reliability is keeping pace with the rate at which we are increasing our dependence on software and the criticality of the systems we are building. The trajectory seems clear. Software will become more complex, more autonomous, more deeply embedded in every aspect of our lives. The potential for failures will grow even as our ability to prevent and manage those failures improves. This is the paradox we must navigate. We cannot stop building software. We cannot retreat from automation. We cannot uninvent the technologies that have become foundational to modern civilization. But we must approach this future with humility, with awareness of the limitations of our understanding, with commitment to learning from failures rather than repeating them. The history we have traced tonight is not just a catalogue of disasters. It is a map of the territory we're navigating, marked with warnings about the dangers that await the unwary, the overconfident, the rushed. As the night deepens toward dawn, as we approach the end of this long contemplation, one final pattern emerges from all these stories of failure. In almost every case, the disaster was preventable. The information needed to avoid the catastrophe existed somewhere in the system. The warnings were there, the concerns were raised, the risks were identifiable. But organizational dynamics, time pressure, cost constraints, or simple human fallibility prevented that information from being acted upon. This is perhaps the most important lesson. Software failures are rarely inevitable acts of technological fate. They are the consequences of human decisions made under constraints with imperfect information by people doing their best in difficult circumstances. Understanding this gives us hope, because it means that better decisions, better processes, better cultures can reduce the frequency and severity of failures, and so we arrive at the heart of the matter. The lessons whispered by these failures across the decades, the wisdom earned through billions of dollars lost and lives forever changed. These are not simple prescriptions or easy answers, but rather profound truths about the nature of complexity, the limits of human understanding, and the responsibilities we bear as we build the invisible infrastructure of the future. The first lesson is one of humility. We must accept that all sufficiently complex software contains bugs. Not might contain bugs, but definitely contains bugs that have not yet been discovered. This is not a failure of skill or diligence, but a mathematical certainty arising from the combinatorial explosion of possible states and interactions in complex systems. The Therac 25's race condition existed in earlier models, but never caused harm because hardware interlocks prevented it. The Ariane 5's overflow bug was invisible until specific flight conditions triggered it. The Night Capital disaster involved old code that had been dormant for years suddenly activating. These bugs were always there, lurking in the shadows of the code waiting for the right conditions to manifest. When we deploy software, especially in safety-critical roles, we must accept that we are deploying systems with unknown flaws, and we must design accordingly, with redundancy, with fail-safes, with defense in depth that does not rely on any single layer being perfect. The second lesson concerns the nature of assumptions. Every piece of software is built on a foundation of assumptions about how it will be used, what inputs it will receive, what environment it will operate in. When those assumptions prove false, disasters follow. The Mars Climate Orbiter assumed both teams were using the same units of measurement. The Patriot missile system assumed it would not run continuously for many hours. The healthcare.gov website assumed that the different contractor components would integrate smoothly. The Boeing 737 MAX assumed that pilots did not need to know about MCAS because it would work transparently. Each of these assumptions seemed reasonable at the time, but each proved catastrophically wrong. The lesson is that assumptions must be made explicit, documented, verified, and periodically re-examined. What was true when the system was designed may not remain true as circumstances change. The third lesson speaks to the economics of quality. Investing in software quality, in rigorous testing, in proper documentation, in adequate time for development, these expenditures often seem like expensive luxuries when deadlines loom and budgets tighten. But the cost of quality is almost always less than the cost of failure. Knight Capital lost $440 million in 45 minutes because deployment procedures were not followed rigorously. Boeing has paid over $20 billion for the 737 MAX disaster that resulted from cost-cutting and schedule pressure. The Y2K remediation cost $300 billion to fix a problem that was created by optimizing for memory usage decades earlier. Time and again, we see that shortcuts taken to save time or money in development lead to vastly larger costs when the inevitable failures occur. Yet organizations continue to make these same trade-offs, betting that they will be lucky, that their shortcuts will not matter. The lesson is not that perfection is achievable or that unlimited resources should be devoted to quality. The lesson is that quality must be valued appropriately, that the true cost of inadequate quality includes not just the immediate development expense, but the expected value of potential failures. The fourth lesson concerns the human dimensions of technology. Software is written by people, deployed by people, used by people. When software fails, it is usually because people made mistakes, not because the technology itself is inherently flawed. The engineer who mistyped a command and caused the AWS outage was not incompetent. He simply made a human error that the system amplified into a catastrophe. The Boeing engineers who raised concerns about MCAS were not wrong, but they were overruled by managers focused on other priorities. The technicians who ignored the Therac 25's malfunction messages had learned through experience that those messages usually meant nothing serious. In each case, reasonable, skilled, well-intentioned people made decisions that contributed to disasters. The lesson is that systems must be designed to accommodate human fallibility, to make it difficult for honest mistakes to cause catastrophic consequences, to create cultures where concerns can be raised without fear, where admitting uncertainty is rewarded rather than punished. The fifth lesson addresses the question of complexity and emergence. As systems grow more complex, they develop behaviors that cannot be predicted by analyzing individual components. The flash crash emerged from the interaction of many trading algorithms, each individually rational but collectively unstable. The northeast blackout cascaded through the power grid in ways that exceeded any single operator's ability to comprehend or control. These emergent failures arise from the architecture of interconnected systems, from tight coupling where one component's failure immediately affects others, from feedback loops where small disturbances amplify rather than dampen. The lesson is that complexity itself is a risk that must be managed, that sometimes the best way to improve reliability is not to add more features or more automation, but to simplify, to reduce coupling, to create systems that can fail gracefully rather than catastrophically. The sixth lesson concerns organizational culture and the normalization of deviance. Standards and best practices do not maintain themselves. They require constant vigilance, constant reinforcement, constant willingness to push back against pressure to cut corners. Over time, small deviations from proper practice become normalized, become accepted, become the new standard. The first time a test is skipped, it feels wrong. The 100th time, it is just how things are done. This gradual erosion of standards creates the conditions for disaster. The lesson is that culture is not static. It must be actively maintained. That organizations must create mechanisms for recognizing when they are drifting from their stated values and practices. That post-mortem analyses of failures must be blameless, but also brutally honest about what went wrong and why. The 7th lesson speaks to the responsibility of transparency. When systems fail, especially when failures cause harm, honesty about what happened and why is essential. The Pentium FDIV bug became a crisis not because of the technical severity of the bug, which was minimal for most users, but because Intel's initial response was perceived as dismissive and evasive. Boeing's withholding of information about MCAS from pilots and regulators turned what might have been a manageable safety issue into a catastrophe that killed hundreds. The lesson is that transparency, especially about safety-critical systems, is not optional. When problems are discovered, they must be disclosed, investigated, and addressed openly. The short-term embarrassment of admitting a flaw is far less costly than the long-term consequences of concealment. The 8th lesson concerns the integration of old and new, the challenge of legacy systems and reused code. The Ariane 5 exploded because code from the Ariane 4 was reused without adequate verification that its assumptions still held. The Therac 25 killed people because buggy code from earlier models was transplanted into a new context that lacked the hardware safeguards that had previously masked the bug. The Y2K problem arose because code written in the 1960s was still running in the 1990s, with assumptions that were no longer valid. The lesson is that code does not exist in isolation from context, that assumptions valid in one context may be invalid in another, that legacy systems require special care and constant vigilance as the world around them changes. The 9th lesson addresses the distribution of costs and benefits. The economic impact of software failures is often borne not by those who made the decisions that led to the failures, but by others. The passengers on Lion Air 610 and Ethiopian Airlines 302 paid with their lives for decisions made by Boeing's management. The cancer patients treated by Therac 25 paid with their health for decisions made by the machine's designers. The customers of Knight Capital, healthcare.gov, and countless other failed systems pay in lost money, lost time, lost opportunity. This misalignment of incentives, where those making decisions about quality and safety do not bear the full consequences of failures, creates moral hazard and contributes to inadequate investment in reliability. The lesson is that accountability matters, that liability must be structured to ensure that decision-makers have skin in the game, that the costs of failures flow back to those who have the power to prevent them. The 10th and final lesson is perhaps the most profound. Software has become infrastructure, as fundamental to modern civilization as roads, power grids, and water systems. But unlike physical infrastructure, software infrastructure is invisible, intangible, constantly changing. We've built a world that depends utterly on the correct functioning of systems that no one fully understands, that contain flaws no one has discovered, that can fail in ways no one has anticipated. This is not a temporary situation that will be resolved when we get better at building software. It is the permanent condition of a civilization built on complexity. The lesson is not despair, but awareness. We must accept that we live in a world where software failures are inevitable, where catastrophes will occur no matter how careful we are, where perfect reliability is unattainable. What we can control is how we respond, how we learn, how we build resilience not just in our technical systems, but in our organizations and societies. These 10 lessons, drawn from billions of dollars lost and lives forever altered, form a kind of wisdom, hard-earned and dearly bought. They tell us that software reliability is not primarily a technical challenge, but a human one, involving economics, psychology, organizational behavior, culture, and ethics. They tell us that the solutions to software failures are not to be found solely in better programming languages or testing tools, though those help, but in how we structure organizations, how we make decisions under uncertainty, how we balance competing pressures, how we maintain standards over time, how we learn from mistakes rather than repeating them. As dawn approaches and our long contemplation draws to a close, we return to where we began, to that graveyard of mistakes built from ones and zeros, from miscalculations and oversights, from small decisions that cascaded into catastrophes. But now we see it differently, not just as a catalogue of disasters, but as a library of lessons, each failure a book written in the currency of loss, each page offering wisdom to those who will read carefully and remember. The future will bring new failures. Systems we are building today contain bugs that will someday cause harm we cannot yet imagine. Technologies we have not yet invented will fail in ways we cannot yet conceive. This is certain. What is not certain is whether we will learn from these future failures as we should have learned from past ones, whether the accumulation of hard-won wisdom will translate into more reliable systems and better decisions, whether we will accept the responsibilities that come with building the invisible infrastructure of modern life. The story of software failures is ultimately a story about us, about human ambition and human fallibility, about our magnificent ability to build systems of staggering complexity and our tragic tendency to believe we have mastered what we have merely constructed. It is a story about the tension between the possible and the prudent, between moving fast and building carefully, between trusting automation and maintaining human judgment. It is a story still being written, with chapters yet to come that will bring new disasters and new lessons. May we have the wisdom to learn before the costs become unbearable. May we have the humility to acknowledge what we do not know. May we have the courage to slow down when safety demands it, to speak up when something seems wrong, to value reliability over expedience. And may we remember that behind every failure, every lost dollar, every shattered system, there are people whose lives were affected, whose trust was betrayed, whose expectations were disappointed. The machines are still humming in the darkness, processing transactions, controlling systems, making decisions. Most of them are working correctly most of the time, but somewhere, in some line of code written today or years ago, a bug is waiting. An assumption will prove false, a cascade will begin, and we will face again the question of whether we have learned enough from the past to navigate the future we are creating. The answer to that question is written not in code but in choices, the choices we make every day about quality and safety, about honesty and transparency, about the kind of technological civilization we want to build, and the price we're willing to pay to make it reliable. Rest now, knowing that the software you depend on is imperfect, understanding that the conveniences you enjoy come with invisible risks, accepting that we have built a world we cannot fully control. But rest also with hope that each failure teaches us something, that wisdom accumulates across time, that we are capable of building systems worthy of the trust we place in them. The night is ending, the machines continue their work, and tomorrow we will try again to build something complex and fragile and essential, a little wiser for the failures that came before, a little humbler about the failures yet to come,